This morning we heard about private clouds and maybe some use of public clouds for science. And this afternoon we're going to start off with a discussion of cloud computing. We have a couple of great speakers. One actually co-created one of the stacks that was mentioned this morning, OpenStack. He's Josh McKenty. He's co-founder and CEO of Piston Cloud Computing. And he was working on Nebula at NASA, and which has since evolved into OpenStack. And then after that, we will have Ryan Boyd, who's a developer advocate from Google, one of the biggest, if not the biggest private cloud in the world now, and how they're actually expanding their services to include things that look like SQL.
I managed to get my favorite time slot, which is immediately after lunch. And the reason being that I am not a scientist, and I am constantly asked to present at scientific conferences, and people are like, can you make it really technical? And that's not really what I do. And so if I show up right after lunch, everyone is asleep. So it doesn't matter if I'm technical or not, but I can be amusing and sort of wake you up, and then the speakers who come on after me appreciate that. So my opinion is, as an engineer, I don't go to conferences to listen to technical details. I'm going to look that up on the web afterwards, and so I am not going to read you any benchmarks. And I'm not really going to talk in great detail about, the number of terabytes or petabytes of this or that database that we managed, or the kinds of processing we did. What I'm going to talk about is the problems we set out to solve at a high level, and the approach that we took to solving those problems, and some of the lessons that we learned, which I think is sort of the most useful part of talking to a human, is to have them tell you what they did wrong, which usually doesn't end up in the publications. How many of you know who Hofstadter is? Wow, love this audience. OK. As the intro mentioned, I was one of the co-founders of OpenStack. It is kind of a thing at this point. So how many of you have heard of OpenStack? OK, cool. It came out of, well, let me back up, actually. Let's talk about cloud as it pertains to dealing with big data or big databases or modern infrastructure, and why that might be a good idea. And it doesn't really have anything to do with efficiency. So I just want to emphasize that. But let's start with a little bit of history. And I think most of this was in the intro, so I'll whip through it. If you have questions, I am a big fan of Q&A, so stand up and ask questions. Please don't throw things. This is my nice suit. Well, you can throw hard things, but not squishy things. We built this thing at NASA that was called NASA Nebula, and we ran it as a service for NASA and for the White House. We hosted some hundreds of projects, and the first projects we hosted tended to be, I think by your scale, not extremely large, but reasonably large. Let's see, the lunar mapping and modeling project, so doing stereographic reconstruction of the surface of the moon, hundreds of terabytes to maybe small numbers of petabytes. The Microsoft Worldwide Telescope project, same surface of Mars, surface of Moon data, transformed and reprojected and streamed to anyone who was using the Worldwide Telescope client. So we had an interesting intersection of large amount of source data, large amount of computed data, and a large amount of bandwidth required to a lot of different end users with kind of the pathological cache miss case. The chance of anybody looking at the same random part of the moon as everyone else, very low. Now, it turns out if there's something really interesting, guaranteed cache hit. The rest of the time, not so much. But because we had no idea what they were going to look at, we had to process everything and keep it all live. So that was sort of the design challenge we went into, which doesn't look much like typical science applications, where you're actually trying to get a result. The result is small, and you can store or throw away the intermediate data. We needed all of that data available online all the time. Ditto for Google Moon and Google Mars. Slightly different relationship. Google dealt with streaming this to the end user. We did the transformation, reprojection, and served it out to them. The hope was that since we were starting with the same source data and really supporting the same kind of end user application, that we could build one infrastructure that would support these two use cases. Because when we started, there was the Google infrastructure at NASA, there was Microsoft infrastructure at NASA. They were mostly idle most of the time, and they were total duplications, different ops teams, different dev teams, different software stacks. So when we're going to talk about this cloud thing we did applied to a set of problems, let's try and get a little more explicit about the problems that we set out to solve. And I said this is not about efficiency, this is about effectiveness. My only, I emphasized before that I'm not a scientist. In fact, I'm not even an engineer. Never went to college. The only formal training I ever had was as a permaculture designer. I don't know how many of you are familiar with permaculture. Fewer people than are familiar with Hofstadter. Okay. Permaculture design is systems thinking for agriculture and societies, but the emphasis on systems thinking, where the performance of a system as a whole is far more dictated by the connection between the parts than it is by the efficiency of any individual part. And this leads to these ideas that effectiveness is about doing the right thing, whereas efficiency is about doing whatever thing you're doing better. So we see this in IT all the time, and it's certainly prevalent at NASA, that they insist on doing everything they're doing better rather than ever stopping anything they're doing, or in fact even thinking about whether they're doing the right things or not. So the supercomputer has to get bigger every year rather than be rethought as whether or not it's relevant to the kinds of science we're trying to do today. With those sorts of statements, you will note I no longer work at NASA. So we have this emphasis on effectiveness, and we have to decide how are we going to measure effectiveness. So we try and keep it as simple as possible. Being effective is about time and money. It is not about IOPS. It is not about total gigabytes stored. It is about the dollars spent and the minutes or hours or days or weeks or months required to get to a result. We decided to look at our own project as a measure of the efficiency and effectiveness of NASA's IT as we set out to improve it. The first thing we tried to do for NASA Nebula was get a virtual machine from central IT to start building an application on. It was going to be a platform as a service application. It took us 6 months to get the first VM. And we decided there was no point in becoming very, very efficient about some other part of the stack because the effectiveness was so low that we needed to go deal with that first. I have spoken at Argonne, at SLAC, at international science conferences in Beijing, at CERN, in the insurance industry, et cetera, and I have never seen an organization that was actually effective. Most people are so focused on efficiency that they ignore the fact that their developers can't get the tools they need in anything close to a reasonable amount of time. And the side effect of this has been that developers are off using AWS, which creates a whole host of other problems. Okay, so we focus on measuring effectiveness, money, and time. I hate giving the same talk over and over again, so this talk I have never given before, and unfortunately they took all of my notes away. So I don't know what I'm going to say until I get to the next slide. So I will be slightly less smooth than usual. But also I'm giving a talk in 2 days on the economics of private cloud. So I'm not going to talk about the money side of this at all today, because I get bored so easily. The specific pain points I mentioned, operations at scale. That was the big problem we were going into of, hey, these are really big data sets. What do we do? Do we use the old tools? I am totally unqualified to talk about operation at scale at XLDB. Most people in the room, including the people coming on immediately after me, have dealt with larger amounts of data and more complicated processing, so I am not going to try and say anything about that. Also, it's immediately after lunch and nobody's awake. However, I will talk about this idea that the problem was application-specific infrastructure. And in other words, if you have a hammer, everything looks like a nail. And if you give everybody in the room a hammer and a big pile of nails, they will build something cool. If you tell every person in the room, what tool would you like, and they're engineers, you will end up with 1,000 different tools, many of which are sort of hammer-like. None of which can be mass-produced, most of which don't drive nails very well because they're designed for a particular dimension of nail, none of which are to any particular standard. And this is really what IT looks like inside NASA, inside most science organizations. Every single application has a different shaped tool that is somewhat but not entirely unlike a hammer. It leads to, when we talk about time and money, the biggest issues with delivering IT infrastructure are headcount and complexity. And headcount is really dictated by how many people are required to work in operations to keep your infrastructure running and to provision it and to manage it and to monitor it and to secure it. The more different kinds of infrastructure you have, the more people are required. So this, as a pain point, led to NASA having a number of data centers that they could not identify, but that were at least 300. A number of security plans, which means the regulatory box around which a server runs, in the low thousands, not really sure. And every single web application framework we could identify being used in production somewhere. Like we originally just did a trade study to say, well, if we were going to provide platform as a service for a single language, what language should it be? Is there an obvious consensus? No, nothing close. There were a lot of people who suggested Lisp. The other one, and the only specifically technical point, and I put this in because Jasek asked me to make this slightly more technical, mobility gap. How many of you are familiar with the term? Okay, I'm glad I put it in here. This is the mobility gap. Everyone's heard of Moore's law, right? This is the improvement of CPU performance over time, theoretical, but we track to it pretty well. Kreider's law is storage density. It is also doing pretty well. Doesn't quite keep up with Moore's law, but it's close. Nielsen's law, which notionally, and for those of you who are scientists in the audience, I am misrepresenting this as being internet bandwidth. It's actually last mile connectivity. But as a rough analog, our ability to move data to where it can be processed and move results back to somewhere where they can be stored is never going to keep up. This is the biggest problem we have in big data. It is very, very poorly understood. The term mobility gap almost nobody's ever heard of. But the reason, this is such a fundamental problem that people think the solution to big data is Hadoop. And they believe that because the MapReduce algorithm is good at moving processing to data instead of moving data to processing. That is the only particular reason that Hadoop and MapReduce has become popular in the big data community, is because it's a good, not great, but good way of dealing with mobility gap. There are other approaches. We tried a lot of them. I will talk a bit about them. I'm going to try and leave enough time at the end for people to be angry publicly on the microphone, but you can also always track me down and be angry later if you want to. So getting into a little bit more specifics, when we talk about cloud, I want to be a little bit more clear about the definition. Cloud is actually 3 different things. And when we're talking about big data, only one of those 3 things is relevant to what we're talking about. So cloud is a business model paradigm that's essentially outsourced and leased services. So anytime you hear people talking about reducing CapEx in exchange for OpEx and the cost of burst and cloud bursting and variable rate of use, that is about the economics of leasing someone else's hardware. That's it. It is not fundamental to the idea of cloud computing. It is fundamental to Amazon's business model, and they spend more dollars on marketing that idea than anyone else. But it's not the most important of the 3. The second facet of cloud computing is the idea that infrastructure should be multi-tenant, shared resources, at some measure of shared. And so for NASA, as a single organization, we have enough diversity internally and enough projects internally that sharing just among other NASA projects is totally enough to achieve the benefits in effectiveness as well as efficiency of using cloud computing. You have to share in order to be more efficient, but you don't need to share with the general public. What you need to do is share with a set of users who have enough diversity of workload that you have some batch processing that could go on separate from real-time processing when real-time processing doesn't need to happen. If you can tuck some sort of day-to-day enterprise applications in there as well to smooth out the curve, so much the better. If you have seasonal things versus constant workload. You don't need to share with total strangers. When we built NASA Nebula, one of the specific design goals was that we should do a better job of sharing with the public. There was this entire open data initiative going on, started shortly after we started the project, and we just got on board. And we never for a moment entertained the idea that we would allow members of the public to use NASA Nebula. That was not a design goal. It's a FIPS moderate system. That's hopeless. Not going to happen. But what would happen is that we built it to look exactly the same at the API layer as systems they were allowed to use. We made the data and the tool chains available by making them open data and open source. We said, hey, if you want to do the same stereographic reconstruction as we're doing in NASA Nebula, take this open source Vision Workbench tool chain. In fact, take these disk images that show you how we run it, set it up, download the data and process it on AWS. In fact, here's the docs for exactly the AWS API commands that you will need to use to do that. It looks exactly the same as our infrastructure. So that was the goal. The third thing that is cloud is API-driven infrastructure, or what VMware is now calling the software-defined data center. That's the part that actually matters. And it matters not for efficiency. It's not about virtualization. It's not about sharing. It's not about a change in business model. It matters for effectiveness. People are slow. Not you particularly. You guys are probably sort of faster than normal people. But people are slow. And if I have to make a phone call to get storage allocated to my project, it's not going to happen quickly. It's certainly not going to happen fast enough to be responsive in real time to the needs of my application. And there's a nasty side effect to this. People are slow and people are lazy, which means if you make me be slow, I'm going to, A, do things preemptively. And I did this at NASA. I was the worst offender. That's why I said we studied our project to see what not to do. When it took us 6 months to get a VM, we held on to that VM for 6 months after we stopped using it. And when it took us 3 months to get a LUN provisioned on the SAN, I asked for a terabyte to start with. And I got it. I got a terabyte. This is XLDB crowd. That terabyte was costing NASA $10,000 a year that I didn't know about. Nobody told me when I ordered it. They're like, oh, here's a terabyte. They also had no idea what I was doing, so they didn't know that I was, in fact, using it to store like 17K worth of source code. The point being, when your infrastructure is not effective, the people involved in that infrastructure make it not efficient. If it takes me an hour to get a VM, just an hour, I'm not going to turn it off when I'm done, because I have invested an hour waiting for that VM, and I don't know when I'm going to need it again. If I can turn a VM on in less than 10 seconds, you can train me to turn it off like a light switch. Turn it on, turn it off. So the effectiveness of API-driven infrastructure is several orders of magnitude more effective than anything that is nearly API-driven infrastructure. And I say nearly when I talk about virtualization. People are like, cloud is just like data center virtualization. No, it isn't. Data center virtualization is nearly API-driven infrastructure. But most of the users of the resources are not the ones who are allowed to make the API commands. And I said allowed. The biggest problem here that we're about to get into is security and compliance. All right, we made some early assumptions about what we were going to do. We did this giant survey of all of the centers at NASA and what everyone was using, and we decided, I wrote a trade study, which you can find on the internet, although it was never officially published, about what language we should use and what language we should support. We came up with Python. Yeah. Why Python? Oh, Woot, okay. Yeah, actually, that was notable enough that I have been made a member of the Python Software Foundation retroactively. Huh? I know. It's okay. I'm okay with that. We made an assumption that we would use only commodity hardware. That comes back to money, and it comes back to reducing the number of systems of record. So I don't want to know whose brand of server it is, which means if we ever use a brand-specific feature, I will fire whoever was involved. We will only use standards. This became difficult when we started using IPMI, because it turns out no vendor in the world actually implements IPMI according to the standard. They all lie about it. On the architecture side, the no snowflakes term was something that our project manager from Booz Allen Hamilton came up with, and they use it internally when they're talking about consultants and how they ought to have every consultant trained up to do every other role. We said, well, that's what we're doing with our servers. We don't have, in fact, by the end of NASA Nebula, we had no database servers. We had no storage nodes. We had no compute nodes. We had no admin nodes. We had no network nodes. We just had nodes. Every service run on every node. When we started doing this, every vendor we talked to and most of the ops team at NASA thought I was insane and wanted me to leave. At the time, we bought a bunch of UCS gear from Cisco, which was like blades, fiber channel connected to external storage, and we refused to use it. And we bought a bunch of 1 and 2U pizza boxes and used direct attached storage. And when we handed ops off, they turned off the direct attached storage, put a filer in the bottom of the rack, and took our total system performance down to like 10% of what we'd been doing with direct attached. So we fired the ops team and went back to doing it ourselves. And you will note I am no longer at NASA. The reason this works, we come back to the mobility gap, right? What are the number of data channels available between your compute environment and your storage environment? Well, if you converge the two of them, it is the maximum internal throughput of your basic network. We did 10 gig everywhere, only copper, and I know a lot of you are probably Mellanox and InfiniBand fans, and I'm going to get myself in all sorts of trouble, but in an environment like NASA Nebula, where we needed to serve data to the public, we needed a lot of outbound internet connectivity. We needed connectivity to SENIC. We needed connectivity to Internet 2. And we also needed as much bandwidth as possible in between the servers. And we really, in the spirit of as simple as possible, we only wanted one fabric. No storage network, no InfiniBand network, separate interconnect, just 10 gig Ethernet, and a separate network for IPMI and management, because inside NASA, messing with security is a bad idea. All right, that diagram, by the way, I'm not even going to talk about. This is what you will notice in this diagram is things by its absence. Okay, there are APIs in the front, load balancers and stuff, and then this auth layer, queue layer, workers. When we first built NASA Nebula, there was no data store at all. So there's storage, object storage, database as a service, but OpenStack itself did not have a data store or need one. State was done by the nodes at the bottom, broadcasting state up to various controllers and cached there. Anytime you store state, you're getting yourself in trouble. Was that a question? No, just waving. Hi. We have since done clever things with distributed file systems and using Zookeeper for configuration data. And when you get out beyond a few thousand servers to tens of thousands of servers, there's some other zone boundary challenges. But the basic spirit is, please try and not have any data store. Question ever having a data store. All right. I have had the term of architect since way before it was cool. And I never thought it was actually cool. And in the last few years, I've started to become uncomfortable and ashamed of being referred to as an architect. Because I don't believe that what we do is design a system and then build it according to that design, and then somehow we got it right. People do not get things right. They oscillate between, hopefully, less and less extreme mistakes. There is a footnote to this, which is that OpenStack was launched in Texas, along with tequila and handguns. Okay, I mentioned before this fully converged infrastructure. I just wanted to highlight this again. We called this Null Tier later on, and we literally run our distributed file system and our virtual machines and our virtual networking and our management control plane on the same servers, on every server, with one class of interconnect. So from an efficiency standpoint, this is a bad idea. There's not a single server that's actually tuned, quote unquote, for any particular workload. Right? We only have one reference hardware architecture. We only buy servers in one configuration, which means we don't use HBAs, we don't use RAID, we don't use IB, we don't use GPUs. We just threw out most of the complexity. From a dollar and time standpoint, operations has almost entirely disappeared. The only operation task is to replace a server with another server. You don't even have to know what it's doing. If server dies, nobody hears it. It doesn't matter. If a hard drive dies, you don't care. It's fail in place. We don't use anything except for distributed file systems. We don't use any externally attached storage. We don't use, like, it is as simple as possible. And you can buy the hardware from anybody now, which means, as far as pricing competitively, HP, Dell, Cisco, IBM, Supermicro, ZT Pro, whoever you want. So if you're buying 100,000 servers, all of a sudden you have an enormous pressure because the vendor is going to come back and say, well, yeah, we could compete purely on price, but we have this other feature. Don't ever use that feature. API first. When it's going to be software-defined infrastructure, the API matters. It is the user experience of your cloud. And you need to think of it that way. And it's both for people to consume and for other software systems to consume. And it needs to be expressive. And it needs to be expressive using the metaphors that your users are going to use. And I'll give a very simple example, and I won't belabor the point. If you use Amazon Web Services, Amazon is built around the idea that every VM is transient, that it can be turned off at any moment, and that you as a user should expect that. In fact, if you're not designing your application to expect your infrastructure to crash, you are a bad application programmer. That is a harsh and unreasonable position to take. There is no way in the Amazon API to turn a VM off without deleting it. Turn the VM off, it's gone. Local disk is gone. The OpenStack API is designed to allow people to build a lot of different kinds of clouds. So of course we have an API that says you can turn a VM off, you can suspend it, you can turn it back on, you can snapshot the local disk, you can publish an SLA in the service catalog around how likely it is that VM would stay up, because most people running OpenStack expect VMs are kind of permanent. In fact, they can be as permanent as you want. You can have reasonable expectations your VMs stay up longer than the servers they're running on. Maybe not the heat death of the universe, but a while. So your API needs to be expressing the right metaphors. I have ranted at like 4 conferences in a row now on metaphors in infrastructure, and I'm not going to say anything about it today other than that we don't have the right ones yet, by and large, and that we're iterating towards them, hopefully by a series of smaller and smaller mistakes. The other thing that's a point when we're talking about convergence and mobility gap and compute and storage and networking is that the APIs across compute and storage and networking need to feel similar. If you're going to expect the same people, being your developers or your scientists or your end users of whatever, to relate to these 3 different sets of resources the same way, this is the DevOps movement or the NoOps movement, those APIs should feel like they make sense to the user instead of to the administrator who is in the process of being put out of work. That turns out really hard. We've been working on that for a couple of years. All right, I talked about security briefly earlier, but I want to come back to it. 80% of the time we spent on NASA Nebula was not on OpenStack and not on training users, although that was the second largest thing. It was on regulatory compliance. It was on getting FSMA moderate in place. And the luxury of building OpenStack, in some cases, over again, there are whole components we've rewritten since we launched OpenStack compared to what we did at NASA, gave us a chance to build them around the idea that if security is an afterthought, your system performance is destroyed in the process of putting the security in place. Because they don't care. It is not their job to care about the performance and the effectiveness of your system. It is their job to keep it as secure as possible. Security in the context of cloud does not just mean authentication, authorization, logging. It means forensics and audit and these sort of more evil, more dirty things. There was a good talk, somebody giving that talk today, actually? No, sorry, that was at VMworld last week. Someone gave a talk on the big data problem of doing the forensic analysis of logs in a cloud environment, which logs themselves become a big data problem, weirdly enough. Rackspace was the first person to point out that the only system they found that was robust enough to handle the log output of the cloud files system that they built was the cloud files system that they built. I think we have seen this effect in other talks. So security in that sense, the assumption you should make going in, if you're going to look at cloud, is you will not be allowed to change anything as far as how your organization does security and you should know as much as possible going in to design around that. You're going to be required to connect to every system that's in place, every system of record. They're going to expect that they can take their typical remediation activities against your cloud environment. On the networking side, for instance, they're going to put stuff into your switch. You better buy a brand of switch that allows them to put stuff into it. We had gone the sort of high performance, like, let's buy cool Arista switches thing, because I love Arista switches, and they're really fast, and they're really cost effective. No, not at NASA. The slide's going to get me in trouble again. The important thing of what we did, actually, I will highlight this by the slide that follows. I'll leave this one be for a minute. When we launched OpenStack, it was successful because we had had 0 committees involved. We did not have a debate about what the API should be. We built one that was wrong, and we made it wrong in a different way. Then we made it wrong in a different way after that. There was no pre-planning. There have been a couple of projects inside OpenStack since then that were extensively pre-planned, totally failed, and had to be rewritten based on solving the first problem that was the most obvious, and then iterating from there. This is not to say that standards work is not vastly important, and that in some cases it's the only way to move forward. But at the edge of IT innovation, standards are horribly premature. So this is why you will see, generally speaking, OpenStack as a 5,000 member foundation now has almost 0 friendly relationships with any other standards body. We just don't believe in standards yet. We will get there later. There are small exceptions. Cloud Security Alliance around Cloud Audit, we've gotten quite involved there because when we're talking about security, we have to go along with the way they do it, which means the standards are already pretty well defined for us, and we're going to go back and implement something that maps. But by and large, the decisions that are being made in OpenStack today around okay, so a very specific example, there is a release of OpenStack that comes out in like a week and a half, 2 weeks, something, 27th, I think, called Folsom. And one of the major deliverables for that release is a rewrite of our virtual block storage implementation and APIs called Cinder, for Cinder block, which was not my idea. And there were no standards discussions about that API layer at all. The design of that API happened in my office on a whiteboard with representatives from the various companies involved in Cinder, so NetApp and Inktank, who make Ceph, and the Rising Tide guys, who make the the Linux iSCSI drivers. And we just got in a room with a whiteboard and said, well, we want to make sure that we can do X, and we think that users are going to want to be able to do Y, and there's this feature at NetApp that people want to be able to still use, and so API has to support Z. And we argued for a few hours, and then we baked something out, we coded it. And later on, we will get around to perhaps getting involved in some of these interesting standards around storage. Certainly not today. Okay. I have generally aimed to have 10 minutes at the end because I figure maybe there's a lot of bubbling rage. I've gone a little short. I have 12 minutes. If there's no bubbling rage, then those of you who have not woken up from your nap yet get a couple more minutes before the next presenter.
Okay, I think we're going to ask people to come up to the mics if it's not too difficult. If it proves
you're in the middle of the row.
Yeah, if it proves.
I'm also pretty good at repeating questions for the sake of the video and the audio. So if you want to yell at me, I will repeat your question and then answer it.
How hard was it to get people like Sullivan versus test versus production at the same time?
Right. So the question is, how hard was it to get developers and test environments and production environments onto the same hardware at the same time? It's a very good question. The short answer, in most cases, so there are several hundred production deployments of OpenStack now. In the majority of those cases, dev and test is run on separate physical infrastructure from production. NASA Nebula, we did them both in the same place. The ops team was very aware of the production requirements of the applications, and the schedulers available for OpenStack. So there's a flavor scheduler, there's a filter scheduler, there's one that was written by NTT that I can't remember the name of. The scheduler's job is to place workloads, whether it's virtual machines or block storage or what have you, on some piece of hardware in that infrastructure. And the schedulers can be defined to use flavors that basically say this is a production flavor or development flavor or test flavor that will place on different hardware or place to different criteria. In other words, don't overload the machines that have production workloads on them as well. That has served well places like Sony, eBay, Mercado Libre, where they've been using this for both dev and test and production environments at the sort of thousands of server mark. But the more conservative organizations for sure are just standing up separate infrastructure, managed by the same API, and then using some orchestration tool in front of those API endpoints, RightScale and Stratus, Scalar, something to move workloads back and forth. Now's your chance. Any questions about OpenStack? No. See, I told you, everybody after lunch, you're all asleep. Do you want me to tell a funny story? The first application we had on NASA Nebula when we launched it was the budget transparency website for the White House, which was a 6 terabyte Postgres database, 6 terabyte Greenplum database, which at the time was basically a Postgres database with a lot of weird things going on. And they had certified that this was ready for cloud deployment, but when they told us what ready for cloud deployment was, they expected the performance of the underlying block store to be sort of better than RAID 5 on SAS drives, which was very hard to achieve as a virtual environment. And so that whole iteration I told you about going from direct attached storage to a filer and then back to direct attached storage, that was what we had to do that for. It was going, hey, we're sustaining 250 megabyte per second write and read on this infrastructure as an NFS export. What do you expect from us? But it was that effectiveness metric, we ended up helping them rewrite the app rather than try and improve the infrastructure beyond any point of reasonableness. And we were able to get like 2 order of magnitude performance improvements out of teaching them how to use caching and proxies and larger key cache in the database. Like there were a lot of other knobs that we turned that made the problem go away. It wasn't actually relevant. That was true in almost every application we worked on. We ended up helping the application developers. And it was never that they needed custom infrastructure. That was the thing. It was not that the application needed custom infrastructure. What it was that the app developer needed to understand the infrastructure they were using. And we found the more we drove that infrastructure to a common standard, the easier it was for them to get familiar enough with that standard to understand the way to work with it. We just stopped changing the playing field underneath them. Yeah. Yeah, absolutely. And so when I said don't have a data store, what I meant was don't have a centralized, highly available, canonical data store for your system configuration, right? So OpenStack itself does now have a database, which ends up being the single point of frustration for everyone deploying it, because you have to treat it like a single point of failure that has to be highly available and has all of these annoying characteristics like getting bottlenecked and having table locks and everything else. Swift, as an example, the Swift component of OpenStack, does not have a single database. It has 3 SQLite databases on every server, and a whole REST API that queries them in this kind of crazy fashion that scales linearly. So yeah, do I think we need to push more and more intelligence into the storage tier? Absolutely. We have prototyped very bizarre data locality aware applications for OpenStack that rather than MapReduce, which sort of gives you a limited set of primitives, you could think of it as a reduced instruction set that will run in place and then reduce functions afterwards. We've prototyped what if you just kind of gave people the power to write any map function they wanted in any language they wanted, and it would be executed inside Swift on the local Swift node with the results correlator back. You get a reduced step afterwards. So basically, you take Swift and turn it into Hadoop. But you can also take Swift and you can turn it into Hadoop by dynamically spawning a VM on the same Swift node. So you have anything arbitrarily you'd put into a virtual machine and use that as your map step. That gets insane very quickly. There are folks going the other direction saying, let's not do virtualization, let's use bare metal provisioning or LXC containers, which also can be managed by OpenStack using the same APIs. And so when you look at efficiency, you say we got to this point where effectiveness, where really the knob that matters is that we're paying a 15% performance penalty by using a hypervisor. Great, scrap the hypervisor. But bear in mind that from a management standpoint, now you have to match kernel versions if you're using LXC. Or if you're using bare metal provisioning, then you have a whole Pixie boot infrastructure, which OpenStack can manage, but again, IPMI is not actually implemented as a standard by any vendor. So you've sort of waded into some operational challenges you're going to have to mop up as you go forward. Yeah. I'm happy to answer that. Do I see a relationship between Open Compute and OpenStack? There are 198 companies involved in OpenStack right now. It represents basically almost everyone who's working on IT, from IBM, Red Hat, Dell, HP, Rackspace, AT&T, all on down to my company. And there are several of those companies who are involved in Open Compute as well as OpenStack. So there are people doing both and combining them in interesting ways. Yeah, I think there's a relationship. Is there a relationship from the OpenStack Foundation perspective? Not really. Efficiency. Open Compute is very much about efficiency. OpenStack is very much about effectiveness. The mindsets are not antagonistic, but slightly separate from each other. And Yahoo is a sponsor of OpenStack, and I spent a lot of time talking with them as we were convincing them to get involved. They know a few things about running large data centers, running a large number of servers. And one of the things they found, there was a point in time where they had better PUEs than anyone. And they found that they'd been focused on turning this one knob. And it had gotten better to the point of being meaningless. And actually, they had sort of half-full racks. They'd focused on super dense environments, and then they couldn't get enough power into the building. The side effects in terms of headcount were such that this improving PUE more didn't matter. So there are some of these cases where folks have a particular workload where that is the most important thing, and Open Compute makes a ton of sense. And there are folks where, I like Open Compute philosophically as this idea of an open hardware architecture for data centers that people can iterate on. The early versions of it, we actually built a baby OpenStack cloud in Jesse Andrews' living room using some Open Compute servers that was called OpenFace Sandwich. Anyway, it was OpenStack and Facebook and whatever. It was funny at the time. It didn't work very well. Just compared to the reference architecture and other hardware we had at the time, it wasn't quite the right mix of components. But I think it has potential. 1 minute and 40 seconds left. Should we have a? Yeah, go ahead.
So you touched on it a little bit in your talk and before the lunch break. There's this gap of going from what I understand to getting it deployed in a cloud or big data or whatever world, so that I can take my expertise and put it in this world with my data and make it work well. Nothing wrong with my application, but I didn't know it could be
So with 1 minute left, I'm going to try and answer this. I think it is the most central question that everybody in this room has to solve. It's the number one thing we talked about at Slack after I was there last week. It's change management, right? What we did in Europe when I was there working for the global earthquake model was we paired up developers with the scientists in charge of the various components. And we had them actually pair program, which is a very uncomfortable concept to take a tenured scientist and say, yeah, we understand you understand the science, but we have to point out your code's not very good. In terms of taking advantage of the characteristics and the platforms available to you. And so we paired up on that, and it worked really, really well. The other way to do it is to climb up the stack and use platform as a service and say, well, if we can stop thinking about some of these pieces and just trust that you need a queue service, use the queue service in the platform as a service, and let the DevOps team figure out which one is best fit. That can work really well. We worked really hard on getting Cloud Foundry working on top of OpenStack. We did a partnership with VMware for that. To try and address this. How do you on-ramp people who are not ready to say, well, I'm going to manage virtual networks. What does that mean? How do I write software that creates networks dynamically for my application? Change management, to quote somebody else, the COO of the New York Stock Exchange was a speaker at a conference I was at in New York. And he talked about the fact that the change management of them standing up a private cloud and moving their application onto it was the only reason they are still in business. They would have been wiped out by NASDAQ otherwise. He had to fire a ton of people to make it happen. Okay, thank you very much.